So here we are in Chapter 6, Part 2, where we talked about the different ways that we can think about computer performance, some metrics and some terminology, and now we're ready to dig into how to actually look at some indicators of computer performance. And we're going to start with the clock rate, which, given everything we've talked about so far, is probably the most obvious indicator. So the speed at which fundamental operations are carried out within the computer is the clock rate. And using the clock rate as a metric to compare processors is probably the worst metric by which to judge computers. But again, going back to a consumer standpoint, it seems to be the one that we've latched onto. And so we could take a look at this figure here that illustrates the CPU clock. And at each clock cycle, the processor carries out an internal operation. And at first glance here, it's tempting to think that the processor's performance is proportional to its clock rate, and therefore the clock rate would be a precise metric. But there are a lot of flaws in this argument. It's not like how the author says it's difficult to know where to begin. So let's start by pointing out that there's no single clock on most computers. There are several clocks in nearly every computer system. And some systems may have entirely independent clocks, such as a separate clock generator for each functional part of its CPU or the bus or the memory. The CPU itself may have several functional units, each driven by its own clock, and some systems have a single master clock that generates pulses at the highest rate required by any circuit, and all other clocks run at a kind of sub-multiple of this frequency, like mini pulses inside of a greater pulse frequency. Another point worth mentioning is that some processors have variable clock rates, right? Mobile processors are probably the most our best example for this. And they're designed for use in things like laptops and in mobile phones to reduce the clock rate to conserve power. So we call this throttling, right? Clock throttling or dynamic frequency scaling. And it's used in a lot of processors today because it is one of the best ways to, just slow things down when the computer's just waiting or kind of, not in a hibernation mode, because that indicates the computer is off. No, actually talking about just like in that wait period when we're not using as much power. And so some processors switch to a lower clock speed if the core temperature rises and the chip is in danger of overheating. This is a protective measure that a lot of processors have, so that if maybe your cooling system isn't working well or the chip is just working really hard, the chip will actually start to slow down as the temperature rises in order to protect itself. So some designers employ clock doubling or even clock quadrupling in order to take advantage of the fact that a lot of people use this as a benchmark. And so we can take a look at this figure here that demonstrates how a clock running at a rate of 2f can be derived from a clock running at a rate of f. And if you delay a clock by 90 degrees and then perform an XOR operation between the original and delayed clocks, you get a new clock at twice the frequency of the original clock. And so we can kind of take advantage of this process. So you can kind of see these pulses here in the figure. And we've talked a lot about how this isn't a great metric. Increasing clock speed doesn't necessarily lead to a linear increase in performance because some actions, right, such as accessing memory, require a minimum amount of time. And if we take a look at this situation depicted here in figure 6.11, where there's 3 cycles required to perform an operation, we can assume that the first clock cycles here are scalable, and we can increase the clock speed and safely assume that whatever is done in a clock cycle is still done if the cycle time is reduced. But in the third cycle here, it includes an operation that requires a minimum time of 52 nanoseconds for its completion. If the clock cycle is less than 52 nanoseconds, the cycle in cycle 3 must be stretched either by slowing the clock or by replacing cycle 3 by 2 or more cycles. So in practice, it's difficult to alter the clock. And it's difficult to alter the clock rate dynamically from clock pulse to clock pulse. And so we use, or most systems implement, a mechanism that extends an operation by an integer number of cycles called wait states. So if we take a look at this figure, we can see the cycle time is 30 nanoseconds, and the 52 nanosecond memory access requires 2 cycles. And the operation now takes 4 times 30 nanoseconds to complete. So the non-scalable clock property of systems that was described by our original figure 6.11 demonstrates why some computers become unstable if you try and overclock them, right? We talked about overclocking as that mechanism, and the author says beloved by hackers. Just about anyone these days can overclock their CPU. It's not a very difficult process. It used to be a difficult and scary process in which you could potentially damage things. But these days we have a lot of software that helps control these systems. We can overclock directly from like software we can install in Windows that helps us manage our CPU. And but ultimately, people who clock processors at a higher rate than that specified by the manufacturer are said to be overclocking. So let's take a detour here for a second. The book points out this white paper written by Shane Rao and sponsored by AMD that talks about, is megahertz enough? Because PC buyers, again, going back to that consumer market, usually rely on the clock speed in megahertz of a PC's microprocessor to determine their purchasing decision. And so because the industry lacks a simple, universally accepted way to judge performance, users have kind of become conditioned to substituting clock speed to gauge how fast their applications will run. But we, at this point, should probably know and realize that that is not a great way to think about anything. And it's become really more common. So the popularization of the PC amongst general consumers has increased the available pool of buyers who are really unaware and uneducated with the factors of PC performance. The growth of the direct model of PC purchases has made it more likely that the actual end user will buy a PC for himself or herself without the help of a third party familiar with factors that influence PC performance. And if increasing sophistication of the PC exposes the buyer to a growing number of often arcane technical specifications from which clock speed promises a convenient escape. So if you've learned nothing else in Chapter 6, maybe you've learned a little bit more about how to be a savvy consumer when it comes to thinking about the types of computer that you want or how to shop for one. But really, that's why this metric has become so prevalent. So, clock rate is a poor indicator of performance simply because there's no relationship or no simple relationship between clock rate and system performance across different platforms. And although we could say System A may exhibit a moderately linear relationship between clock rate and performance over a given range of clock speeds, System B's performance may have a very different relationship between its clock rate and performance. So, clock rate might help us compare two Type A systems and two Type B systems, but it does not allow us to compare a Type A system with a Type B system. And I hope you realize I'm just talking very abstractly here, right? Type A and Type B. We're not talking about anything specific, but just to help you understand how this does or does not work, right? And so the author talks about how they read one time, to their horror, a review of a popular computer magazine that stated the G4, which was found in Apple's Macs, was inferior to a Pentium processor because the G4's clock rate was substantially less than the Pentium's clock rate. But such an argument, when we actually understand the system architecture, is nonsense. The Pentium may or may not be better than the G4, and the reviewer was entirely wrong to presume that the performance is directly related to clock speed across different platforms, and that a processor with a higher clock speed is faster than one with a lower clock speed. And so this is really where we've been derailed as consumers a little bit, and that the clock rate, it might be a prime metric that will live on, or it may become increasingly irrelevant as the internal architecture and organization of processors that execute IA32 code continue to diverge, and clock rates continue to stagnate, because that's what we're starting to see, right? I talked about, the book says 2008, really it's 2010. Clock speeds have really ceased to follow that Moore's law and increased dramatically because of the limits of power dissipation, which goes back to heat, right? And so power dissipation is proportional to the square of the clock frequency. And so to get around this, manufacturers have really started to direct their efforts towards multi-core processors rather than faster processors. So if we can't make them go faster, how do we just put more of them in there? And so clock speeds may rise again if power consumption falls because of the introduction of maybe a new semiconductor material, or because circuit innovations such as asynchronous clocking, where circuits are not driven by a master clock, one event triggers another, right? And asynchronous circuits can operate at up to 70% lower power levels than their clocked counterparts, but really design, testing, and verification is problematic. So without breakthroughs is really where we're at with engineering. We're kind of, I'm not going to say stuck, but it is going to be interesting to see what's going to happen when manufacturers can't lean on that number being bigger to show themselves up to the competition. So let's talk about MIPS. A slightly better metric than clock rate is millions of instructions per second, or MIPS. So this metric removes the discrepancy between systems with different numbers of clocks per operation by measuring instructions per second rather than clocks per second. So let's take a look at this formula here for a given computer, where N is the number of instructions executed and T execute is the time taken to execute them. And so the MIPS rating, it's a poor metric that fails for the same reason as the clock rate, right? A MIPS rating tells us, only how fast a computer executes instructions, but it doesn't tell you what's actually achieved by the instruction being executed. So we can take a look at this hypothetical example of computation on two computers, right, A and B, where computer A has a load store architecture without a multiplier, and computer B is a memory to register architecture. And so computer A is more verbose than computer B. And we can take a look at this table right here that we're looking at, these two types of instructions. Both computers can evaluate the expression z equals 4, and then we have x plus y, right, in the parentheses. And so suppose computers A and B have the same MIPS, right? So we've scored them exactly the same. They execute code equally rapidly. If we relied solely on MIPS as a metric of performance, we would have to conclude that the computers offer the same performance. But as we can see, computer B is faster than computer A because not only the 4 instructions that are required to do the work, right? And this argument is based on the assumption that all instructions take the same time. Really, in practice, computer A might be faster than B because memory to register architectures are slower than register to register architectures. And so this is where we struggle. The MIPS metric is also sensitive to the way in which a compiler generates code. So the duration of a single instruction is cycles, right, multiplied by T cycle, where cycles is the number of machine cycles required to execute the instruction, and T cycle is the cycle time, which is usually that clock period. So the total execution time for the program is given by this equation that we can see here. So Ni is the number of times instruction I occurs in the program, and Ci is the number of cycles required by instruction I. So if we plug this formula into our MIPS equation that we see here at the bottom, this is what we can get. So really this expression tells us that the MIPS value is affected by the instruction mix, right? The nature of N, and the length of each instruction executed, which is that C term. And if an instruction mix consists of a large number of instructions with one cycle, the MIPS value might be high, even though the actual code is executed more slowly than an instruction mix that contains a lot of multiple cycle instructions. So here's another example. We can say, this program is compiled to run on a computer, and the compiler generates 2 million one-cycle instructions and 1 million two-cycle instructions. So if we assume that the cycle time is 10 nanoseconds, the time taken is given by, and here you can see where we've plugged in all of the values. Now suppose that a different compiler generates code for the same problem, but with a 1.5 million one-cycle instructions and 1.2 million two-cycle instructions. In this case, the time required to execute the code is a little different. And so we can see that here in this equation. Sorry, I was trying to get out my pen. So the second compiler generated faster code. So if we look at the MIPS, right, first case and second case, the faster computer has the lower MIPS, even though it's clearly superior to the slower computer. So really, this failure of the MIPS metric is inevitable because instruction throughput does not take into account how much work each instruction actually performs. So if we recall that the time required to execute code is given by the CPU execution time equaling the instructions multiplied by the clock cycles per instruction multiplied by the clock period. So each of these terms is dependent on a particular set of design criteria, and each of these criteria can be independently optimized. So consider the number of instructions per program. The size of a program depends primarily on the instruction set architecture. We've already seen that a CISC processor can execute complex instructions such as operations on bit fields that require many separate instructions on a RISC processor. And so another factor that helps determine the number of instructions can be executed is the number of the compilers. Let me back up. Another factor that determines the number of instructions to be executed is the nature of the compiler that generates the instructions. And so some compilers can generate more efficient code than others. And so the number of clock cycles per instruction is a function of the processor's internal organization. And as we look further into computer organization, right, we can see that there's a relationship between the instruction complexity and the number of clock cycles required to execute an instruction. And if we consider the design, right, of a shifter that moves bits one or more places left or right, the computer engineer can design a shifting circuit to shift, right, and make that shift register in a one clock cycle by using maybe a barrel shifter. A shift register uses a chain of flip-flops. And really the point comes down to there's always going to be some kind of simple trade-off between time and circuit complexity. Right? And we've learned at this point that a clock period is governed by three factors. We have our device physics, the ability to dissipate heat, and the chip's logic design. So the rate at which signals propagate through that semiconductor devices, right, can be improved only by shrinking the device or by changing the semiconductor's electronic properties. And when a signal changes level in a chip, it's necessary to change our inter-electrode capacitances of the transistors on the chip. Now, I know that's probably a really confusing statement for some of you if you're maybe have never taken like an electrical engineering class or you're not really familiar with like any of this terminology. But really what this explains is the process requires energy, and raising the switching rate increases that power consumption. So since all energy eventually ends up as heat, increasing the clock rate causes the chip to become hotter. So that's really where we've come down to. Heat is our limiting factor, and the heat can be dissipated only via conduction to the outside. So consequently, the maximum clock rate is often limited by the ability of the system to dissipate heat. This is where we are stuck. So let's take a look at an example. All right, we have a benchmark running on a hypothetical RISC processor, which gives us the results here in table 6.3. And we can obtain the cycles per instruction for each class of operation by multiplying the relative frequency of the instructions by the cycle per instruction to get the values down here in table 6.4. So we should be able to see the relationship here, frequency multiplied by cycles. We can also relate the relative instruction frequencies to the percentage of time an instruction class takes by multiplying the instruction class frequency by the number of cycles and dividing the result by the average cycles per instruction. So if we take a look at table here, 6.5, the register load instruction takes up 20% of the code, but is responsible for 45.71% of the processor cycle time. So this is telling us that loading registers from memory is expensive. This figure here helps us sum up the relationship between clock rate, MIPS, instruction count, and our computer system design. So the concentric layers represent the components of a computer from its technology, so things like fabrication and silicon, to the programs that run on it. The three ovals that we can see in blue represent the factors that affect the performance of the system. So these are things like clock rate. And so this figure demonstrates approximately the relationship between the design layers and the performance factors. So, for example, the manufacturing technology determines the maximum clock rate, whereas the compiler has no effect on clock rate. Next, we're going to talk about MFLOPS. MFLOPS stands for millions of floating point instructions per second. And it's similar to MIPS, except for MFLOPS counts only floating point instructions, or floating point operations. In principle, the same objections to MIPS can apply to the MFLOPS metric, and therefore we might expect MFLOPS to be poor as an indicator of performance, as MIPS is. But in fact, MFLOPS is a better metric than MIPS because MFLOPS measures the work done rather than the instruction throughput. So MIPS counts all instructions executed by the computer, many of which perform no useful work in solving a problem, so like data movement operations, whereas MFLOPS considers only floating point operations, which are really at the heart of the algorithm being implemented. So no matter how fast our computer is, the MFLOPS metric will be 0 if the program contains no floating point operations, and MFLOPS is most useful in comparing computers used in scientific applications where numerical calculations dominate the computation. Now, one of the biggest downsides to MFLOPS is that computers don't implement floating point arithmetic in the same way. Now, I might go over your head here for a second, but just bear with me. Things like Galati points, he points out that in scientific calculation, right, the number of or the nature of the program and its data has a profound influence on an MFLOPS rating. So, for example, let's talk about math for a second. When comparing two computers, one system might yield a better rating for calculating or with the MFLOPS calculations involving like sparse matrices, and the other might yield better results for calculations involving full matrices. So MFLOPS is also useful in comparing maybe special purpose processors, such as like digital signal processing, which are chips that are used in embedded applications to process audio and visual signals in real time. But it's not, again, easy to calculate because it's really not standardized. So what all of this comes down to is that MIPS and MFLOPS and clock speed do not perform or provide a uniformly reliable metric. Sometimes, as we've seen, the ordering of the various metrics is consistent across different computers, and sometimes they even contradict each other. And so before we look at a more universal benchmark, let's take a quick break to discuss a law that is at the heart of computer performance. And this is Amdahl's law. And this is probably by far the most famous law governing computer performance. It's an infamous law because it appears to place a limit on the maximum performance increase that can be achieved by optimizing a computer subsystem. Clearly, improving part of a system can increase the system's overall performance. So for example, you can reduce the time of a journey that involves a flight following by a car ride by increasing the car's speed without changing the length of time spent on the aircraft. So Amdahl's law describes the performance increase that you get when a program is run in a system where some of the operations can take place in parallel. This law tells us that what performance increase you get for greater parallelism, and it's applicable to any system where you are interested in the effect of local improvements on the system globally. So we could say that Amdahl's law highlights the effect of bottlenecks in a system. So let's take a look at a figure that helps us illustrate this a little bit. So this effect of parallelizing part of an activity can be seen here in figure 615. The diagram demonstrates that the serial, irreducible part of the process remains the same, while the parallel or reducible or improvable part of the system is reduced. So ultimately, system performance is dominated by the serial part of the system, and the motto of the computer designer has become, make the common case fast. So let's take a look at an example. Suppose a computer executes a program on a single processor in time, So we'll represent this with t to the s seconds. And if we have p processors and the program is divided into p equal chunks, then the same program will run t seconds over p seconds. So assume that a fraction of the program, represented here, can run on the p processors, and that the fraction can run only on one processor. So our execution time on the parallel computer system would be represented this way. So the speed up ratio for this system is the ratio of the speed without parallelization to the speed with parallelization. So what Amdahl's law tells us is that the speed up varies, from 1, where we have our no parallelism, to p with perfect parallelism. So more importantly, it teaches us the law of diminishing returns, which you may already be familiar with. It's really a limit in the bottleneck of system performance by which attempts at further improvement are futile unless that bottleneck can be removed. So we can take a look at a couple of cases here in this table 6.9. So our fraction of a program is 0.2 and 0.1 respectively for various degrees of parallelism. And the speed up ratio falls off rapidly once the serial part of the process begins to dominate the equation. In the limit, an infinite number of processors cannot make the speed up ratio greater than the reciprocal of the fraction of the time devoted to serial processing. And Amdahl's law illustrates the effect of a bottleneck on system performance and shows us that there's a limit beyond which attempts at further implementation, again, are futile. So that brings us to benchmarks, The ideal program with which to evaluate a computer is the one you're going to run on that computer. And that seems so kind of intuitive, The computer should be configured in exactly the same way in which you're going to use it. So if it's a workstation, a personal computer does not just run a single program, but it executes a mix of programs that change from moment to moment. If it's specifically like a scientific-based computer, then of course you want to prioritize speed of mathematical calculations. If it's for video encoding, then of course you want a processor that's designed to handle that and prioritizes that kind of calculation. So one approach to benchmarking is based on kernels or fragments of real programs that require intense computation, such as the LinPack benchmark. Another approach we have is to run synthetic benchmarks that are programs constructed for the express purposes of evaluating computer performance and which purport to be similar to the type of code that users might actually execute. And these are the kinds of benchmarking operations that we see when you want to like test your memory or test your GPU. They simulate the environment by which you are running the application that you might actually run, and it kind of gives you some scores and some outcomes. And benchmarks can be divided into two categories. We can have the fine-grained and the coarse-grained. And the granularity of a benchmark is a function of the object being measured. So for example, a benchmark that measures the performance of a complete computer system can be considered coarse-grained, whereas a benchmark that measures the performance of like branch instructions would be fine-grained. And fine-grained benchmarks measure the execution rates of specific instructions rather than entire applications or kernels. And so sometimes we call these micro benchmarks. So what this comes down to, and hopefully what we understand at this point, is that benchmarks have to be interpreted carefully. We have to know what is being measured and how those measurements have been carried out. And a set of benchmarks may demonstrate that one computer is far better than another, and in practice, these benchmarks may be entirely misleading if your workload does not match the benchmark. And suppose the benchmarks rely very heavily on pure CPU processing power, and the target application involves large databases or disk-based input-output. The benchmarks would have little relevance to the actual application. And so for many computer users, benchmarks are irrelevant. So in today's entry-level computers, they're largely untaxed by the workload of the average user. Most people are so overpowered for their application, it's ridiculous. And so word processing, spreadsheets, web surfing, modest levels of image processing can perform with little to noticeable delay. Even software developers, for the most part, are usually over-geared. And for many users, the bottleneck is the internet connection, of which they have very little control. Or in gaming, right, it could be the GPU, which requires, high level of computational performance, is the bottleneck by which any other processing would fall behind. So really, a little history, right? From the 1990s onward, a large number of what we could kind of consider to be ad hoc benchmarks appeared in popular personal computing journals. These kinds of benchmarks were really intended to simulate the type of work people would carry out at home or in small offices, and they were really weighted towards computationally intensive programming like rendering images or video compression. And these kinds of PC benchmarks, they're not often created by like academic groups or international bodies. We could talk about the SPEC benchmarks in just a second. But PC benchmarks are constructed by like magazines that review PCs or by those that have like similarly oriented websites. Maybe you're familiar with some of these, like the bhardware.com PC benchmarks. 3D Studio Max had one. Really, the interesting, you can go look at some of the figures that each kind of successive generation of microprocessor has generated on some of these types of benchmarks. But again, they're frequently aimed at those who use PCs in demanding applications such as state-of-the-art computer games or multimedia. And there's a lot of data out there on like how different types of processors perform. And what I find is interesting is that each successive generation of microprocessor is faster than the previous generation, and that within a given generation, the speed increases with clock frequency. So the slowest members of a new generation of processor may be slower than the fastest members of a previous generation. But remember that the fastest members of any generation often have a very high price premium. So there's always going to be those kinds of trade-offs. So since most of those benchmarking applications come from people who are trying to sell you something usually or contain some kind of bias, either kind of implicitly in that they're not designed for really what they're trying to measure, or explicitly in that they're cherry picking information to try to make their stuff look better, Let's talk about the SPEC. So there are various organizations that exist to offer consumers unbiased advice, whether it's about the quality of wine or the safety of automobiles. And the organization that we would want to focus on in this case is the SPEC, which is the Standard Performance Evaluation Corporation. And they are a nonprofit organization with the status of a charity that's really been formed to establish, maintain, and endorse a standardized set of relevant benchmarks that can be applied to the newest generation of high-performance computers. So it's important to note that the SPEC benchmarks are supplied as source code, and then they're compiled. And the user is responsible for compiling the benchmarks before they're run, and the SPEC allows two types of compilation. One type is restrictive in terms of compiler flags and switches that provides a base result. And the other type of compilation is a little more liberal. It allows switches to be optimized for individual programs or kind of performance metrics. And this provides what we call a peak metric. And so the SPEC consortium develops suites of benchmarks intended to measure computer performance, and new benchmarks are created by SPEC as technology develops. So these members, they develop the test programs, and of course, some members might be tempted to create benchmarks that exploit special features of their own products, but scrutiny by other members of the consortium really helps to reduce any product bias in the benchmarks created by the SPEC. That doesn't keep them from changing the benchmark to hide deficiencies they all share. So there's a good example of this. Where they had benchmarks that showed poor branch predictor performance in CPU 95, and they were dropped in CPU 2000. So branch predictors were generally weak at the time, and it was in nobody's interest to continue demonstrating that. And so these SPEC benchmarks, they can have an effect on compiler writers. Since compiler writers are likely to use SPEC suites to test their compilers, it's probable that some compiler writers will tweak or tune their compilers to the characteristics of the SPEC programs. And so as much as we try to get away from these kinds of bias, and where things happen like SPE suites change to remove some of the inefficiencies and errors, right? And there's a lot of examples of that as well. We always have to be kind of cognizant that this kind of manipulation might be happening. And so the rapid growth of computer technology in the late 1990s really caused SPEC to expand its range of benchmarks. They included some new market items that are like specifically by Java, and programs in Java are normally compiled into bytecode and then executed on a bytecode interpreter known as the Java virtual machine. And so there was a benchmark suite that measures computer system performance for Java virtual machine client platforms. And then by 2001, they were writing very specific benchmarks for CPU-intensive applications. They had the Application Performance Characterization Project Group that released its first standardized benchmark for evaluating performance systems running 3D Studio Max. So we started getting into kind of highly specialized type benchmarking. So the advantage of a benchmark such as the SPEC is that it's widely available, it's relatively easy to obtain, they provide real results on real data rather than simply relying on metrics such as clock rate or MIPS or inflops, and that at best do not tell the whole story, or at worst are positively misleading. Now, if you want to dig into their methodology, it is quite math intensive, but it is open. You can just go out there and read about it and kind of see how it works. I encourage you to do so if you're interested in that kind of thing, but it may be very much over your head if you have not maybe taken some higher level mathematics. So the rest of our chapter really kind of digs a little more in depth into how the SPEC works, a little bit about their averaging and weighting, as well as how the academic community uses some of these benchmarks, which I think maybe is fascinating, but I don't really think I want to drone on and on about that too much. So really, this is the end of chapter 6. And so let's talk a little bit in summary about what we learned here, because this chapter, I think at this point, is a little different from what we have been doing so far. We've really been digging into hardware. We've looked at assembly programming. Now we're starting to talk about things in a little more abstract way. And at one time, right, we were just happy with a computer if it worked. I mean, I say that all the time. I wish technology would just work. But today, we're interested in performance because some of us want to design faster machines, and because we wish to buy machines with the highest performance, and then of course for the lowest cost. And so in this chapter, we've really looked at some of the various ways of comparing the performance of machines. And hopefully, I mean, again, if you've learned nothing else, we know that the processor's clock rate is the crudest of all metrics. Different processors cannot be compared on the basis of clock speed at all. And simply because clock speeds tell us nothing about how the processor behaves internally, things like the MIPS metric goes kind of one step further in telling us how fast instructions can be executed, but again tells us nothing about how much work the instructions actually do. So looking at, enthusiast PC benchmarks designed for the power user or the enthusiast, or professional program suites like SPEC that are popular in academic and commercial worlds, right? Power really has become the key criterion in computer design, partly because of the growth of battery-based mobile computing and partially because of the need to cool our computing equipment. And we can expect to see power become increasingly important as a performance metric, and companies advertising computers on the basis of their processing power per watt. I definitely think that that's something where we're going, because again, what are those marketing people going to do when they can't point at that bigger number anymore? So some of you might feel a little disappointed at the end of this section on performance because we've not been able to define a simple single measure of performance that actually works. And of course not. Each user has his or her own way of defining performance, and what matters is that the current performance measurement techniques contribute to progress in computer design. So this has been the end of our chapter 6. I hope you've enjoyed learning about this and that you'll continue with our course.